This is Where We Live from Connecticut Public Radio. I'm Lucy Nalpathanchel, broadcasting remotely. We've spent a lot of time on the show diving into how the coronavirus pandemic has affected our lives and will continue doing so. But what are researchers working on that will one day give doctors effective treatments for people hospitalized because of COVID-19? And what efforts are underway now to develop a vaccine to prevent deaths from this highly contagious disease? Today, Where We Live, we talk about the science behind the coronavirus. Coming up, we learn more about how viruses work and what scientists have learned about this particular coronavirus. And what questions do you have about coronavirus? You can join us, 888-720-9677. That's 888-720-WNPR. As always, find us on Facebook and Twitter at Where We Live. Now, my guest joining today via Zoom, Carl Zimmer, a columnist for the New York Times and the author of 13 books about science, including A Planet of Viruses. Carl also lives in Connecticut. Carl, welcome back to the show.
Thanks for having me.
Also with us is Dr. Ellen Foxman, assistant professor of laboratory medicine and immunobiology at Yale School of Medicine. Dr. Ellen Foxman, welcome to the show.
Thank you very much.
Well, I wanted to start off with Carl, so let's break it down and go right back to the basics. When we talk about the coronavirus and other viruses, how do they work exactly?
Well, viruses in general are just a sort of you can think of them just a bundle of genes that's in a tiny little package. It might be a protein shell or sort of an oily membrane. And what they do is they get inside of our cells, and then their genes basically take over our cells, and the cells make new viruses. That's the gist of being a virus, and different viruses do that in different ways. And so coronaviruses are a bunch of different species of viruses that are all related to each other, and they all basically look alike, and they all basically work in the same way. They tend to be respiratory viruses of humans and other animals. And so, if you've had a cold, it could have been a coronavirus. And this just happens to be a new type of coronavirus that probably moved into our species sometime late last year.
Before we talk more about this new coronavirus, there was some confusion recently about the nature of this germ causing COVID-19. At a press briefing last Friday, President Trump appeared to confuse the viral infection with diseases caused by bacteria. This is what he said.
They develop drugs like the antibiotics. You see it, antibiotics used to solve every problem. Now one of the biggest problems the world has is the germ has gotten so brilliant that the antibiotic can't keep up with it.
So, Carl, when you heard, or as you're hearing the president talk about this germ and mentioning antibiotics, because this is a virus, antibiotics, they can't work against a virus. Can you describe again how they're different than other germs that cause disease like bacteria?
Yeah, so this is, it's unfortunate when the president is spreading misinformation. Let's just get that out of the way. It's incorrect to think that we are dealing with bacteria. Bacteria and viruses are fundamentally different things. Bacteria are kind of like our own cells in the sense that they actually grow and divide like our cells do. And they're much bigger than viruses. And so you can take penicillin to kill off viruses, there we go again, bacteria, because it interferes with their growth. Viruses don't grow, they just take over our cells. So, this is a problem when we're not in the middle of a pandemic. Your kid is sniffly and you go to the doctor and you really want the doctor to do something for your kid. And so you really insist on antibiotics. Well, if the kid has a respiratory virus, the antibiotics aren't going to do anything. Now, this is a total distraction. There are antivirals that can interfere with how viruses replicate, and there are some that actually work very effectively against, say, HIV and hepatitis. And scientists right now are trying to find them for the coronavirus. That's a totally separate thing.
Dr. Ellen Foxman is with us as well on Zoom. When we heard Carl mention different viruses like the common cold, we also know about the flu. What is it about this particular coronavirus that has made it so deadly?
Well, that's a great question, and there's a couple things. One thing is about how the virus works and causes disease, but another really important thing is the fact that it's a new virus to the human population. So I'll talk about that part first. So as many people are familiar with the idea that when you get infected by a germ and it causes a disease in your body, your immune system recognizes that and remembers that germ for the next time. So starting a couple weeks after that infection, your immune system has pre-existing defenses to protect you against getting that same virus again. And that's why you mentioned common colds and flu. Sure, those are similar in that they infect through the nose and throat and cause some similar symptoms to this new virus, but they're different in that many people in the population their bodies have seen that year after year, and many people have pre-existing defenses against it. This new one, because it jumped over from an animal into humans late last year, as Carl mentioned, the issue is that at that time, late December of last year, let's say, no one in the whole globe had pre-existing defense against this virus. And that's what allows it to spread really rapidly from person to person, and also to potentially cause a more serious infection in a person who doesn't have pre-existing defense. And that's why we're so worried about flattening the curve and social distancing, because we're trying to slow down that spread so the hospital system doesn't get overwhelmed. So that's the main, I would say that's a major difference, and why the difference between a pandemic and these flus and cold viruses that come year after year. And the second part is, how about this virus compared to, let's say, the common cold virus? Rhinovirus is the typical common cold virus. Well, it infects a different part of the body. So all these viruses come in through the nose and throat. And a lot of these viruses are pretty mild and taken care of by the body's natural defenses for a lot of people, but there's some vulnerable group in the population who can get really sick. And for rhinovirus, the common cold virus, most people, they get a mild infection, but people with asthma get really bad constriction of their airways, and so they can get seriously ill. In the case of this virus, it seems the very vulnerable people are people who already have problems with their heart and lungs, because this virus can attack the lungs. And if you're borderline in your lung function already, it can cause very serious illness. So those are the two main differences between some of the common colds that we see every year.
We're talking about the science behind coronavirus on the show today on Where We Live. You can join our conversation if you have a question, 888-720-9677, or find us on Facebook and Twitter at Where We Live. Carl Zimmer, let's talk more about what scientists know about this particular coronavirus, how it's made up, how it actually attacks cells. A lot of that has to do with the way it's shaped. Some people may have seen these images, the spiky ball. Can you describe what we're seeing?
Sure. So what you're looking at is this tiny kind of oily bubble with little protein spikes on it. And scientists actually call these proteins spike proteins. And when the virus gets into the airway, those spikes can kind of latch on to certain proteins that sit on some of our cells. And it's a little bit like a key turning a lock, and that allows the virus to basically fuse to our cells and dump in its genes. It's got 29 genes or so, which is not a lot, but that's all it needs to take over our cells. Our cells have sort of natural, antivirus defenses, and some of the virus's genes actually can knock those defenses out, and then we start making these new copies of the virus. A cell will spill out millions of new viruses, which can then infect other cells in the airway, and that either we fight it off, as Dr. Flaxman was saying, with their immune system, or those viruses just overwhelm the system.
When we talk about overwhelming the system, there's a listener on Twitter who asks, why does the coronavirus kill the old but not the young? What's going on with the interaction between the coronavirus and the immune system that explains this difference? Ellen, I'll go back to you.
Yeah, sure. Well, that is a very interesting and important question, right? As I was mentioning, different different of these viruses that come in through the nose and throat sort of target different vulnerable populations. And this one, it seems to be particularly bad for the elderly, and especially for people who already have problems with their lung function. So why is that? Well, there's two different ways the viruses can cause, serious symptoms. And as Carl was mentioning, one important way is they get into your own tissues, take over those tissues, and make more copies of themselves. And in the process, they destroy the cells that they're using to make those copies of themselves. So they directly damage the tissue. And then the other thing that happens is the immune system senses that there's something bad going on and starts to mount a big defense response. And then you basically get like a war going on. So the immune system, cells from the immune system come to the area to fight the virus. And wherever that war is going on, there can be collateral damage. So if that war is, if you just have a cold in your nose and that war is going on in your nose, you're going to have like the runny nose and the congestion and so forth. If that's happening in your lungs, you can get very serious symptoms of, real difficulty breathing. And so there's one possibility that probably both things are going on in the people who get seriously ill. One is that direct damage to the lung. If you're young and healthy, maybe a little bit of damage to your lung isn't going to affect your overall breathing that much because you have a lot of reserve. Whereas if you don't have much reserve, that damage might cause some, you might, if you're someone who can, go jogging 10 miles versus someone who has trouble walking up a flight of stairs, and then you have a little problem with your lung, that's going to be a lot more serious for the person who has trouble walking up a flight of stairs. And then the other thing is the immune response. There's a lot known about in young versus old people. There's differences in the immune response. And part of the damage this virus caused seems to be for people who get seriously ill because of the wrong kind of immune response getting triggered, and the kind that can cause a lot of collateral damage. That they're starting to see that in the patients who are seriously ill.
I think some people might have seen this in print, the cytokine or keen storm. Is that how it's said?
Yes, cytokine storm.
Okay, thank you. And this is an immune overreaction.
Exactly, yeah. So there's some drugs that specifically block certain of those cytokines are basically chemicals that the body uses to communicate that there's a problem, to get cells of the immune system to come to the lung and fight the infection. But if that's an overreaction or the wrong kind of reaction, it can actually be harmful as well. So there are actually drugs. One of those cytokines is called IL-6. I don't know if people have seen that in the news, but there's a drug that specifically blocks that. So that's one thing people are trying, like, can we not stop the immune response, but can we shift it a little to a more helpful one instead of a harmful one?
Carl Zimmer, I wanted to go back to you. We heard Dr. Ellen Foxman talking about, again, late last year, where there were reports of this new coronavirus. What do we know about when we think about where this particular coronavirus first popped up, but then we think about the epicenter in this country being the New York City area? What scientists have learned looking at the virus's genome and where a lot of this illnesses here in this part of the country trace back to?
Yeah, so the genetic material in this virus actually kind of acts like a sort of a history book. It records its own history because every time that viruses make a copy of themselves, there's a chance that the genetic material will mutate a little bit. And when that virus then replicates again, that mutation gets passed down. And so if you read the genetic material, the genome of these coronaviruses, and you compare them, you can see like, oh, this bunch of viruses all share the same mutation, and these share a different mutation, and these have 3 mutations that none other have, and you can actually draw a family tree. And that tree actually like takes you all the way through this whole story. A lot we don't know, but we can see the kind of the rough outlines. And so you can see, for example, that the closest relative to this virus lives in a bat. It lives in a Chinese horseshoe bat. It's the ancestor of that bat virus, and this human virus existed a few decades ago. And so that was the ancestors of this virus were then living in other bats and mutating and so on. And at some point, they gained the ability to be pretty good at living in humans. It seems all of the genomes in humans basically point us back to an origin in China in late last year. You may hear people saying, oh, there was coronavirus in California in the fall and I had it. And no, all the evidence points against that. There's no evidence supporting that. So it was in China. And then from there, it started to spread to other countries. Now, New York, as you mentioned, has been slammed by this virus. It's tragic. It's horrific. And so, scientists are saying, okay, how did this happen? How did we get here? And so they're looking at the viruses in New York and they're comparing them to viruses in other countries. And what they find is that that this virus was repeatedly introduced into New York City and Connecticut, as a matter of fact. It seems to have been happening at least in mid-February, maybe early February. And if you trace it back to the countries where it immediately came from, it's mostly Europe. Not Italy, but it seems to be the closest matches are in places like England and France and Belgium. All that means is that there was a lot of virus going around in Europe, and then people were traveling from Europe to New York. There were some that were coming from Asia as well, but not that much, it turns out. And so now scientists are going to be tracing these mutations forward. They're going to see, like, well, how is it spreading within the United States, country to country, town to town?
Carl, when we talk about the virus mutating, what do scientists know about when we see these slight mutations? Is it making the coronavirus more potent?
There's no evidence that these mutations that scientists are seeing are making the virus more potent or making it different in significantly different strains, which is great news, because what that means is that, when we try to find antivirals or vaccines, we don't have to be thinking about 3 or 4, 8 different viruses that we all call this coronavirus. It basically, like, we've got one target and it's not changing that fast. So if there's a little bit of good news in this terrible situation, that's it.
What you wrote recently about how the virus's genome from this epicenter where people were getting coronavirus in this part of the country being traced back to Europe, that actually got the attention of President Trump when we talked about misinformation. He tweeted about it. He was confused and thinks it's strictly coming from China. But as you mentioned, when we trace back the genome from cases in this part of the country, because of travel from Europe, that's where we saw this transmission.
Yeah, it's kind of weird to be tweeted at by the most powerful person in the world, especially when they totally get your story wrong. I have no idea if he read it or not, but he, again, was spreading misinformation. The fact is that if you look for where the virus, showed up from in New York, is people on planes, mostly from Europe. But, he was tweeting that, like, I was just using unnamed sources or something like that, which is, again, just a way of insulting the New York Times. All my sources are named just because scientists tend to be okay with being on the record. In any case, I responded to his tweet and tried to set things straight, at least for other people, if he's not going to pay attention, and people can see my article for themselves.
I think,
and they can see the data too, because the New York scientists in Mount Sinai have actually posted their data publicly, and there's a website everyone can check out called nextstrain.org where they're tracking the virus as it spreads around the world. It's an amazing exercise in public science, and everyone can check it out.
I think the tweets that you sent back to the president's tweet were very diplomatic, but the very important sentence that you started out with, I'll read it. It's important that you and everyone else understand the science of COVID-19 because people's lives depend on it. We'll make sure we link that at Where We Live. Dr. Ellen Foxman, I wanted to ask, when we hear again about this particular coronavirus and how it is so contagious, when we think about other viruses that have caused problems, SARS, Ebola, why again are we seeing this particular disease having such an extraordinary impact around the globe?
Yeah, that's interesting. Ebola was very, very fatal I think it had something like a 70% fatality rate, but it didn't spread very much. It was sort of like in the area where it began, either people died or they became immune pretty fast. And so we haven't seen that kind of spread. And with the SARS, the first SARS coronavirus back in 2003, what was different about that than this virus is almost everyone, like 99% of people who got that, had a fever for a few days before they really got sick. And so there was this huge signal that somebody was about to be able to spread this disease, which is they got a fever that you could measure. And so it was much easier to know who might be contagious because you could just monitor people's body temperature and say, look, if you have a fever, you got to stay away from people. But this virus is not doing that. So there was a study of like over 40,000 people in China that looked at sort of the spectrum of illness from asymptomatic and mild to serious to critical. And about 80% of the people at least fell in the asymptomatic to mild category. So if you don't know that you're sick and you don't have a fever, you don't have a cough, you don't know to stay away from people. And that's why it can spread a lot more easily. Now, I have heard people talk about it's really bad news that this virus can be asymptomatic, but I mean, there's also a flip side to that, which means it's possible you could get infected, not get very sick, but still get immunity. And so that's not a bad thing. I mean, it's not necessarily bad that the virus isn't killing everybody that it infects, So I think that there's two sides to that coin of a lot of people having asymptomatic or mild infection.
Just one more question before we head to break. Carl Zimmer, we've been seeing a lot of different numbers about the death rate from this coronavirus, different statistics from one country to the next. Is the virus more deadly in some places than others, or is the data just wrong?
Well, the data is the best that we can manage in different circumstances. If you're there are all sorts of things that go into how you basically come up with that fraction. How you want to know, well, how many people have the disease. That's not so easy when we have this in the United States. We have this terrible shortage of tests still. We're not testing anywhere near enough that we should. So there could be lots of people, well, there almost certainly are lots of people who have it who are not being recorded as confirmed cases. And then, then there's the question of who's dying. It turns out that, certainly in New York City and some other places, like there's a lot of people who are dying at home who might very well be dying of COVID-19 and they may not be tested for it. So we have a rough kind of a rough sense of this. I think that this is going to be the subject of a lot of research to come. But the healthcare systems also make a big difference. If you don't have enough ventilators, more people are going to die.
This is Where We Live from Connecticut Public Radio. I'm Lucy Nalpathanchel. My guest today on Zoom, Carl Zimmer, a New York Times columnist and science writer. Also, Dr. Ellen Foxman, assistant professor of laboratory medicine and immunobiology at Yale School of Medicine. Coming up, as scientists work on a vaccine to prevent COVID-19, certain drugs have gotten attention as possible treatments for people hospitalized because of the disease. We talk more about those treatments, and we'll take your calls too. 888-720-9677. That's 888-720-WNPR. As always, find us on Facebook and Twitter at Where We Live. This is Where We Live from Connecticut Public Radio. I'm Lucy Nalpathanchel. You've probably heard more now about the anti-malarial drug hydroxychloroquine than ever before. Multiple media have reported that there's now a shortage of this drug as people like President Trump tout its effectiveness to treat people dangerously ill from COVID-19. But is this really an effective treatment? What do researchers know about this drug? My guest today via Zoom, Carl Zimmer, a New York Times columnist and science writer. Also, Dr. Ellen Foxman, assistant professor of laboratory medicine and immunobiology at Yale School of Medicine. Before we talk about this particular drug, let's talk more about the kinds of medicines that can tackle a virus. Carl, for viruses, there are antiviral medications. How do they work compared to, again, when we talked earlier about antibiotics that work for bacterial infections?
Right. So antivirals, like the kind that people can take to cure some forms of hepatitis or to control HIV, what they do is they actually interfere with the virus itself. They kind of jam up the virus's protein so that they can't do their job. And so they make the virus their target. And there are a whole bunch of antivirals, some of which are used for other viral infections in the clinic, some of which are still being researched, that are all now being pushed into actual, formal clinical trials for COVID-19. And, we might actually be finding about some of the earliest trials pretty soon, which is heartening. They might work, they might not. We don't know until they actually do good clinical trials. There are other kinds of drugs that actually would actually interact with our own proteins in a way, sort of making it hard for the virus to use our cells. And some people have speculated, and I'm just saying speculated, that chloroquine works that way. But there's no evidence from a clinical trial where you compare chloroquine or these versions of chloroquine to people not getting it to show that it's actually effective. There's none of that yet. And so, doctors may decide to try it out sort of as a compassionate use kind of approach. They're doing that with a lot of different drugs. But, people should not be assuming that this has actually been proven to work. It hasn't.
Dr. Ellen Foxman, we heard Carl mention that you need to have effective drug trials to know if a particular medicine will work against something like COVID-19. So talk us through what is an effective drug trial, because we know time is of the essence.
Yes, that's a really important point that Carl made about in the news, we've heard about hydroxychloroquine, other things like zinc and anti-parasite drugs and things, that there's a glimmer they may work, but there's no proof. So I guess the first question is, what do we consider proof? Like what the FDA would consider proof that a drug really works is a randomized controlled trial. And what that means is basically you have a lot of people, not 10 people, not 20 people, but hundreds of people. And then they're all at the same stage of the disease, and as far as you can tell, they're all similar. And you give some of the people a placebo or a sugar pill and the other people the medicine. And they don't know which one they're getting, and their doctor doesn't know what they're getting. You might hear double blind. That's what that means. They don't know whether they're getting the sugar pill or the drug, and neither does their doctor, because even thinking you're getting a medicine can make you report that you feel better. So to really be blind, and then and then at the beginning of the study, the doctors say, okay, I'm going to look at this endpoint. For example, I heard of a study that's going to be starting in New York and Pennsylvania about hydroxychloroquine. And what they're going to do is, for example, get people who are in their first 48 hours of the illness, of the symptoms, and then give some people the sugar pill, some people the drug, and say, our endpoint is, do people need to come to the hospital less if they've gotten the drug as opposed to the sugar pill? Does it make a difference in if they can just stay home and get better? So that's an example. There's a lot of different endpoints you can use and different populations you could test, but that has not been done for a lot of these drugs that we see in the news. It has not been done yet. It's starting to be done now for sure. And it won't take that long, because now we have a lot of cases, and we can see in a couple weeks that person would either end up in the hospital or not. So it won't take that long, but we don't have the information at this moment.
Max on Twitter asks, how do we attempt novel therapeutic approaches without putting patients' lives in jeopardy? Ellen?
Oh, yes. Well, I think this is how, right? We do a real trial, like what's being done now, where people have the opportunity to get enrolled. And I want to point out, even though there's no effective there's no new antiviral medicine that's proven to work yet this way, there are a lot of effective medical interventions that can be done. I mean, as far as preventing the illness, we all know about, reducing your exposure, but also keeping your body healthy, not smoking, those kinds of things. And then if you get sick, as I said, this virus is really attacking people with weak lungs, or weak heart and lungs. And there's a ton of very proven effective medical therapies to support the heart and lungs through stress. There's drug treatments that can support the heart and lungs. There's hospital care, which is vigilant attention to someone's vital signs and adjusting things, giving people oxygen, and even, in an extreme case, the ICU and the ventilator. But those things are proven extremely effective intervention. So it's not like we don't have anything to help patients. We do have a lot. We just don't have a targeted antiviral yet.
We've been hearing a lot, again, as we mentioned, about chloroquine or hydroxychloroquine. The Connecticut Department of Consumer Protection announced last week the state received a donation of hydroxychloroquine for use by the state's hospitals from a drug company. We've heard that there isn't a lot of evidence to show that this particularly helps COVID-19 patients. There might be some symptoms. That's why they're trying it. But what does this mean when we're hearing about people stockpiling this drug when there's people with other conditions, Carl, like lupus and other autoimmune problems where they're not able to get this drug?
Yeah, I mean, this is a real serious issue. I mean, if you are hoarding hydrochloroquine because you convinced yourself or someone else has convinced you that it's going to save you from COVID-19, there are going to be other people who you're leaving in a really desperate situation, people for whom this drug is really important. And not only that, but one thing we should also bear in mind is that hydrochloroquine is not some sort of simple, easy drug. I mean, it can have side effects depending on how much is used, and it's involved in heart arrhythmia and other things. So just thinking that this is going to be a panacea, that you just pop some hydrochloroquine and you're fine, is not the case. And so, if it would be great if a clinical trial shows that this is really effective. But if that's the case, then we need to have sort of a national or international strategy for making more of it if it works out. But if people are just taking this and it's not doing anything to help them and might even be harming people, then that's a terrible situation to be in.
We're talking about the science behind coronavirus with my guest today on Zoom, Carl Zimmer, a New York Times columnist and author of 13 books about science, including A Planet of Viruses. Also, Dr. Ellen Foxman, assistant professor of laboratory medicine and immunobiology at Yale School of Medicine. You can join our conversation, 888-720-9677. That's 888-720-WNPR, or find us on Facebook and Twitter at Where We Live. Carl, there's a lot of attention on vaccine development. We hear that it could take more than a year for scientists to develop a vaccine. Meanwhile, people are being asked to still social distance. Data Haven says Connecticut adults are saving 400 lives by avoiding non-essential travel today. I mean, this is something that I think still needs to be stressed to people because there are no effective treatments or vaccines that have been isolated to date.
Well, I mean, let's flip that around. There are effective treatments, and everybody who's staying at home, everybody who's staying 6-10 feet away from anybody else, anybody who's doing these things, anyone who's washing their hands, they are helping to save lives. As you say, hundreds, thousands of lives. The worst projections where scientists were saying, well, what happens if we just don't do anything? We are flattening that curve. That means that people's lives are being saved, and we should be proud of that. And it's hard being at home, and for some people it's really hard. And if it's a consolation, just remember that a lot of people's lives are being saved right now. The long-term solution, as you say, will be for a vaccine. Mm-hmm. And people have to remember that the average time that it takes to develop a vaccine is like 15 to 20 years. The record for a vaccine for mumps, I believe it was 4 years. So now there are over 100 projects going on right now around the world to develop a COVID-19 vaccine. And some of them are, let's say, if everything goes right, we could be looking at a vaccine starting to roll out in a year and a half. The stars have to align, but it's an amazing undertaking that we're seeing right now. People are marshaling everything they've learned about vaccines over the past 200 years to try to get this thing out as fast as they can. But it's not going to be out tomorrow. And in the meantime, we have to be thinking about things like classic things like social distancing, and maybe we can talk later about contact tracing and all these sort of more traditional ways of holding an infection in check.
And we'll continue to talk about that right after the break. I'm Lucy Nalpathanchel, and this is Where We Live. You can join us too. Find us on Facebook and Twitter. This is Where We Live on Connecticut Public Radio. I'm Lucy Nalpathanchel. My guest today, Carl Zimmer, New York Times columnist and author of 13 science books. Also, Dr. Ellen Foxman, assistant professor of laboratory medicine and immunobiology at Yale School of Medicine. Right before the break, Ellen, we were hearing Carl talk about other strategies to think about treating this disease, something that's been talked about in the news. Researchers are looking at using antibodies from people who've recovered. What can you tell us about that?
Yes, that's an interesting idea. So that's called passive immunization. And the idea there, I guess let's take a step back and just talk about what an antibody is for a minute. So as I was saying before, one reason this virus is spreading so fast is because none of our bodies had seen it before in the whole globe when it jumped into humans. And what does happen, though, is after you do get infected with a germ, your body, your immune system remembers that infection. Your immune system has the ability to make specific chemicals in the blood called antibodies that bind to the virus. Like basically they recognize the shape of the virus. And when you get infected again, those antibodies can bind and coat the virus and prevent the infection. So there's an idea that, there's a couple things that are really interesting about this antibody thing. One is if we could get a really good test for those, we could see who's already been exposed and already made an immune response. And leaping forward even beyond that is if we can see that someone's recovered and they have these antibodies in their blood, could that be used to treat somebody who's very, very ill? And in fact, in the 2003 SARS epidemic in China, that was used, that strategy called passive immunization, or just taking the antibodies from someone's blood and giving them to another person. So there is an idea to do that. There's been a few examples where that's been done in the U.S. so far, maybe a handful. Again, it's in the realm of experimental treatment. Sort of if you don't have a proven therapy for something and someone's very ill, you sort of want to just try something that might work to try to save that person. So in those cases, you leapfrog ahead of those randomized controlled trials I was talking about. So there have been some situations like that where it's been used. And certainly that's one of the many things people would like to try. And there are studies going up in the US to try that as a way of helping people who are severely ill.
Carl, Dr. Ellen Foxman said something that I wanted to hone in on. She said, if we had a really good test to see who has these antibodies, and that's the stickler, right? Trying to find an effective test that would be able to see if this will be an effective way to help people maybe even go back to work, as we hear more and more politicians talking about sending certain people in the workforce back to the office.
Well, let's not get too far ahead. I mean, I know we all want life to go back to normal, and we want to sort of pin our hopes on anything, so we want to pin our hopes on an antibody test that will totally, show exactly who can go back to work and be totally immune and so on. And there are a few problems with that. Dr. Foxman can address this because this is, part of her job these days, which is that, excuse me, these tests are, they're pretty good, but they're not really great, so they might tell you have the antibodies when you don't, or they might say you don't have the antibodies when you do. I mean, it doesn't happen often, but when you have a situation where maybe a few percent at most of the population actually has gotten the virus so far, if you want to know yourself if you've been exposed, that's not great. So we're waiting for a test that really you can really trust on an individual basis. But even if we were to get that test, we don't know that much about immunity. We're sort of waiting and seeing. There are these worrisome reports out of South Korea and other places that people who tested positive for the virus and then seemed to recover, then later tested positive again. And people are saying well, did they get reinfected? A lot of scientists think no, this is probably just a problem with the testing for the virus itself, and that could be. But we need to sort these sorts of things out. And then how long does the immunity last? Does it last a month? Does it last a year? Does it last your life? We don't know because it's a totally new disease. So, people should not, just as people should not think that we already know of a panacea to cure this thing, they should not think that we already have a test that is going to just totally make you totally at ease about having been exposed.
That's an important point that you bring up, Carl. In Connecticut, Governor Lamont has talked about his hopes for antibody testing in this state. He just had a call with business leaders last Thursday saying they expected to roll out an antibody testing program in the next 2 weeks, focusing on first responders and manufacturing workers. Dr. Ellen Foxman, did you want to add to what Carl had talked about?
Yes, I think that is a very important thing to address. And, it's sort of human nature, especially when we're all stuck in this disrupted state where we're staying at home, we can't do our normal jobs and the economy suffering. You want to think how are we going to get through this and how are we going to get back to work? And it's really great that so many people are working on that. As far as pinning all the hopes on antibody testing, that I don't think that's a wise course of action. I like the idea of using your informed common sense and taking all the information together. The issue is, as I said, when people get infected with a virus, they often form these antibodies, which are chemicals you can detect in the blood. But there's a lot of unanswered questions. I mean, the first thing that people may not realize is if you have a mild infection, at least in the few studies that have been done, it can take 3-4 weeks before these antibodies are detectable in the blood. So if you're waiting for somebody to, and especially with the current test, which may or may not be that sensitive. So if you're waiting for someone to get that test to be positive to allow them to go back to work, that could be really hindering you in terms of, that's not the only information that you need. It could even take longer for those antibodies to appear. So that's the problem with false negatives. And on the other side, false positives, so getting indication that you have this antibody and that you're immune, there's a couple problems with that too. One is that, as I mentioned, this antibody works by detecting the shape of the virus. But we also talked about that there's other coronaviruses in the same family that cause colds every year, and they have very similar shapes to this coronavirus. So you could be detecting antibodies to one of those, which doesn't necessarily mean you're protected from the COVID-19 virus. And another issue with there's also the unanswered question that Carl alluded to, which is just because you have an antibody doesn't necessarily mean that you can't get infected again. It has to be a protective or neutralizing antibody. And that's a more complicated thing to measure. And so that's going to take longer to figure out. I think the big picture situation here is normally these kinds of tests are developed for months before they would be used for an actionable decision. And because this is all so new and happening so fast, we're in the situation where we have to start using these tests, see how they work, and kind of reevaluate as we go. It's like you're trying to navigate, but you're still drawing the map and having to erase things and correct the map while you're navigating. So that's the challenge.
Before I ask a question from a listener on Twitter, Dr. Ellen Foxman, when a vaccine is developed to fight this particular coronavirus, could you explain why there are some vaccines where we get lifetime immunity, but other types of diseases we have to get a booster or keep getting particular shots every year?
Yeah, I mean that's a good question. I mean, I guess the best example is the flu shot, right? We know when we're little kids, we get immunized against measles and things like that, and then we never have to get that again. But the flu, we have to keep getting a new vaccine every year. And that's actually because the flu virus can change quite a bit from year to year. So that's a situation where if the virus is the type that can change quite a bit from year to year, then you really aren't super protected by the previous shot that you got. Now, it doesn't look like this coronavirus, at least at the moment, like it changes that fast. So that's a good thing. The other issue is, like, sometimes you do need a booster. Like, we know for tetanus, we get a booster every 10 years. And that's just something we'll have to figure out. The immune response is a little bit of mysterious, even to immunologists, in terms of each new virus and each new vaccine. And so it's just something that would have to be monitored and followed up on. But it's totally doable. We do that all the time. We do that for hepatitis vaccine. You can just measure the antibodies 10 years out and things like that. So that's not a huge barrier if there needs to be a booster.
Our Carl Zimmer, we just have 3 minutes left. Chris on Twitter asked, post-pandemic, what needs to be done to strengthen infectious disease preparedness and response at local and state health departments?
Well, we need stronger local and state health departments, for one thing. We need a much stronger national public health support. We don't spend very much on it. Think about it. I mean, this virus has wiped out trillions and trillions of dollars of economic value. We spend maybe a few $1 billion all told on public health, and we need to be thinking much more seriously about how we prepare for the next one, because there will be a next one. There are lots of coronaviruses flitting around in other animals. There are lots of other kinds of viruses too. We're putting pressure on the ecosystems where these animals live. We're going to have another spillover. We need to be monitoring these animals. We need to know about these viruses. We need to have capacity to build vaccines really fast. We need masks. We need lots of masks. This is ridiculous that we're having doctors wearing garbage bags. It's absurd. So there's a whole lot that we have to do now and looking forward.
And Dr. Ellen Foxman, last words from you as we close out the show, something that you really want to stress to people.
Well, I guess one thing that to end on a positive note, one thing that has been amazing as a scientist involved in virology research is to see the huge pace of scientific discovery and information sharing during this epidemic, partly because of the internet and partly just because of the state where our scientific research endeavor is. So actually, I feel very encouraged when I see that the virus is discovered in December and then the whole sequence is available and there's a test or ability to test a few weeks later. So I really think that that's one positive note, is just the role that science can play in actually helping us fight this.
Well, we thank both of you for a really interesting hour here on Where We Live. Dr. Ellen Foxman, Assistant Professor of Laboratory Medicine and Immunobiology at Yale School of Medicine. Also, Carl Zimmer, New York Times columnist and author of many books, including A Planet of Viruses. Thank you both so much for calling in today.
Thank you.
Thank you. Thank you for having me.
Today's show, produced by Carmen Baskoff. Our technical producer is Kat Pastor. I'm Lucy Nalpathanchel. Thanks for listening.